The main difficulty was that Faraday's field concept was extremely hard to grasp because fields are intangible by nature. Today, we take for granted that concepts like electric and magnetic fields are fundamentals and cannot be reduced to something else. But it was far from obvious for the scientists at that time. Static force, as charges were not moving. Because, in Ampere's and Newton's approaches, one object's motion can be affected by another object even without the two being in physical contact. Attitudes that had developed through his education at Edinburgh and Cambridge. Electrostatics, forces between static electric charges. 2. Magnetostatics, forces among static magnetic materials. 3. Electromagnetism, magnetic effects of electric current as discovered by Ørsted. 4. Electromagnetic induction, electrical effects of changing magnetic fields as discovered by Faraday himself. A source from where water is spreading out. The divergence at that point is positive, and you have a sink where the water is coming together. The divergence there is negative. Elsewhere, there's no spreading or gathering, and the divergent sources and sinks. Divergences are used everywhere in fluid dynamics, electromagnetism, and vector calculus. Suppose you drop a tiny twig into a flowing river. If the twig starts spinning in place, there is a curl at that point. Fluid is that its divergence is zero. This allowed Maxwell to immediately write down the interpretation is that, unlike electric fields, there are no positive or negative magnetic charges that could act as a source or sink. Magnetic poles always come as a pair. Divergence of the electric field is equal to the charge density. This is the second Maxwell equation. In the fluid analogy, the positive charge regions correspond to the source of the electric field, while the negative charge corresponds to the sink. These two equations are also called Gauss's law for electric and magnetic fields, though Laplace was the one who first wrote it. I agree. The namings are quite weird. Gauss's law can be used to derive Coulomb's law and vice versa. The main limitation of this fluid analogy was its inability to explain the interactions between electric fields, magnetic fields, and electric currents. Maxwell's first two equations described only static charges.